All of us. Now this is part 3 of electromagnetic induction. In the first lesson, we learned about Faraday's law and Lenz's law. We realized that when we exert a bit of force with a magnetic field, we can generate electricity. So that's when we go on to part 2 of our lesson, where we talk about how we can make use of this Faraday's law and Lenz's law to generate electricity using an AC generator. And for today's case itself, we would like to talk about the transformer, which is another application of using electromagnetic induction. Okay, so for a transformer itself, uh, most of us have not seen a transformer, but it's actually available in all our everyday life. Any of your electrical appliance itself requires a transformer because the main supply voltage that is coming out from our plugs is 240 volts. But for example, for the laptop that I'm using now itself, I think it requires about 18. Let me see. How much does it need? It requires 20 volts. Okay, it requires 20 volts. So 240 volts is too much. We need 20 volts only. So we need to actually change it, bring it down. Okay, so let's understand more about transformers. So for transformers itself, although the main supply voltage we receive at home is 240, different appliances requires different. CD player runs at 12 volts. I don't think you know what's a CD player already. TV runs at 110 to 240 volts. In my laptop for this, it requires 20 volts. How you do? You know, there's always this brick that you see, okay, for your laptop. Not sure if you're able to see it. They always have the voltage that is required for your device itself. So in order to convert the main supply voltage, we need to make use of a transformer. So you can read up on Faraday's iron ring experiment on textbook page 435 to find out more about what Faraday do with this iron ring experiment. But in simple term, we can make use of this iron ring itself to actually channel the magnetic flux. So what is a transformer? A transformer is a device that changes a high alternating voltage to a low alternating voltage or vice versa. We know from the power equation that if you have a high voltage itself, you have a low current, and you have a low voltage itself, you have a high current. So what is this transformer used for? It is used to, number one, transfer electrical power from power stations to household. If you've been to Malaysia, you've been to certain areas like Bukit Timah Hill, you can see that there are power cables running overhead. These are cables used to transfer power from power stations to household. Another one is also to regulate voltages for usage. Example, for my laptop, I have the device there to transform whatever is coming out from the main electrical supply to power my laptop itself at a correct voltage itself. You do not want too much, you do not want too little. So how does transformer look like? This is a closed core transformer. A closed core transformer consists of two coils, the primary coil and the secondary coil, each with an appropriate number of turns. These coils are wound around a laminated soft iron core. So it's basically an iron core, but they place sheets and sheets of it on top of it, either such is stacked into a core. Okay, why do they want to place thin sheets itself? Before that, each of these sheets are insulated from each other by a coating of lacquer. Why do you want to use a lamination and not a block? Because a block itself will introduce more heat loss. So by having pieces of this kind of iron and place them side by side such that they do not touch, it reduces heat loss due to induced eddy currents. You can read up more about eddy currents by Googling. It's basically just currents in your iron that flows in other direction that causes it to heat up. Okay, so the transformer works on the principle of electromagnetic induction, as I mentioned at the start, and this is how they are like. So will a direct current or alternating current be set up in the secondary coil? We can see here that there's an alternating voltage at the primary coil. When there's an alternating voltage, what will happen is in here there will be an alternating magnetic field. When there's an alternating magnetic field being produced by this coil, there will be an alternating magnetic flux through the iron core. When there's alternating magnetic flux, here it will generate an alternating electromagnetic force or EMF, and there will be an alternating current being formed. So yes, the alternating current will be formed at the secondary coil at the load itself. So in the transformer, the number of turns is directly proportional to the voltage that's being produced. If we want to increase the voltage, we should have more turns. If we want to decrease the voltage, we need to decrease the number of turns. If we increase the number of turns to increase the voltage, we call it a step up. If we decrease the number of turns to decrease the voltage itself, we call it step down. And this is the general relationship. Vs divided by Vp equals to Ns divided by Np. Vs means secondary potential or secondary voltage. Vp means primary voltage at the primary coil. Ns means secondary number of turns at the secondary coil. Np means the number of turns at the primary coil itself. Usually Ns over Np is also what we call as the turns ratio. Next, power transfer in a transformer. A lot of questions are usually asked, what is one assumption that you make when you use this transformer? We assume that it is ideal. That means in the good place itself, there is no heat loss. We assume it's 100% efficient. Power supply is fully transferred to the secondary coil. Nothing is lost. So if nothing is lost itself, we will obey this equation because we know that the power at the primary coil is equal to the power at the secondary coil. So P equals to IV. Vp, voltage at primary coil, Ip, current at primary coil, Vs, voltage at secondary coil, Is at current at secondary coil. So if it's an ideal transformer, there's no power loss, there's 100% efficiency, this is the equation that will govern it. If there is 100% efficiency, we can, this itself will give us an efficiency N of 1, but if it's not efficient, then we need to calculate how much is it being produced at the end, the output, over the initial amount that is being put in, then you times 100%, then we know the efficiency. Okay, so some of the power laws are illustrated below here. So example, when you use your coils itself, there is heat loss because your wires, remember, have resistance, and when there's resistance, heat will be lost. So that's where some of the power will be lost. Next, there is also heat loss in your iron core when there is eddy currents. Remember, eddy current is just currents that don't flow in the correct direction, magnetic flux that don't flow in the correct direction that cause eddy currents to be produced, and that this will be lost as heat in the laminated soft iron core sheet. Next, when there is during the linkage itself, some of the magnetic flux may be leaked as it flows along, or maybe it may move away or may be lost. That's where power also can be lost. At the same time, there's hysteresis loss caused by the flipping of magnetic dipoles in the iron core due to the AC. Because there is alternating current itself, the electrons that flow through itself have certain properties within them that you have not learned this level that cause it to actually flip, and it will cause further power loss called hysteresis loss. You can actually Google more about this. Okay, so these 4 factors itself will actually cause the power loss when we use a transformer. So let's make use of this. So for example, a transformer has an input of 240 volts. This is Vp. There is a current Vi flowing in the primary coil. Not Vi. This is your Ip. It's found that the output voltage is 12 and there are 50 turns in the secondary coil. So if this is a step up or step down, we look at the voltage. We realize that voltage drops. We know that this is since the output voltage inside coil is less than the input voltage, we know that this is a step down transformer. How many turns are there in the primary coil? We use the equation Vs divided by Vp, Ns divided by Np. Put in the numbers. Vs is 12, Vp is 240, Ns is 50 because that's the second number turns. Then we find for Np, realize that Np is 1000 turns. Why is the current flowing in the secondary coil? What is the assumption made? So you see there's an assumption, assuming that this is an ideal transformer, there's no power loss, there's 100% efficiency. We use the equation Vp Ip equals to Vs Is. We put in that initially in the primary coil there's 240 volts. Okay, the current is 2 milliamperes times 10 to the power minus 3, that's milli. Voltage is 12 volts, and then you can find for the current. So in this case, the current is 40 milliamperes. Okay, so when electricity is transmitted from a power station to our homes, we want to reduce the loss of energy through Joule heating. Joule heating is simply when electrical current passes through your wire itself, it causes the cables to heat up. Okay, this is called Joule heating. So this is when the current flows. So we want to minimize this heat that is being lost due to current flowing in the cables. We want to minimize this efficiency and make sure that it's cost effective. So how do we make sure we minimize it? We must first understand Joule heating can be calculated how much energy that is lost when this current flow through the cable using this formula P equals to I square R. Okay, we will use this and not the other one, which is V square over R. We will do not use this, we'll use P equals to I square R. Why? Because of the nature of Joule heating itself due to the movement of current. That's why we will need to focus on current I and the property of the material, which is a resistance. Okay, so one way to calculate this, one way to reduce this effect is to use thicker cables, but when you use thicker cables itself, it can be more expensive. So what is another way? Another way is first you must understand the formula for your cable. Okay, R equals to rho L over A. Remember that the longer the wire, the more the resistance. The thicker the wire, the lesser the resistance. Okay, and the rho here itself is the resistivity. If you use thicker wire, yes, you can lower the resistance, you can lower the amount of heat loss through Joule heating, but the cost will increase because now you want to make thicker wire, you need more material, it will be heavier. Imagine you want to hang a heavy wire overhead. Okay, imagine Malaysia, Malaysia, there's this overhead cables itself. If you were to hang a heavy wire above that, it will drop down, it's very dangerous. Okay, so another way to reduce this effect itself, if we cannot change R, is to change the I. Because remember, there's two factors, there's R and there's I. If we cannot change the R, we want to change the I. So what we want to do, reduce the current flowing. So how can we reduce the current? We can reduce the current by using a step-up transformer. So when the electricity leaves the power station, we want to step it up. Okay, so the whole idea here is we want to have a higher voltage. By having a higher voltage, we lower the current, and then we will have a smaller loss of power. So at the same time, higher voltage also raise the cost of insulation, but it may not be as expensive or as dangerous as compared to using a bigger wire. So how do you want to increase the voltage such that we have a lower current? With lower current, then we have lesser power loss due to the formula. How do we rise the voltage, increase the voltage? So let's look at an example here. Your power station comes out about 100 kilowatts, which is a very, very big amount of power. Okay, a step-up transformer increases the voltage in the transmission line to 20,000 volts. So there is 100 turns of wire in the primary coil. So this is MP. Increases the voltage in the transmission line to. So this is your secondary. Your voltage that's in the secondary coil. And 20,000 turns in the secondary coil. So this itself is the number of turns in the secondary. They want you to calculate the voltage in the primary coil. That means what is the voltage that is put in when it leaves the power station. So imagine power station goes into a transformer and then it leaves through your cables, your transmission cables. So this will be your step up transformer. Okay, so they want you to find what is the voltage that is coming out from your power station before it enters the step up transformer, because that is where your primary coil is. So you use the equation, you put in your numbers, you'll find that VP, the primary coil, is 100 volts. That means when it comes on a power station, it's only 100 volts. Calculate the current flowing in the transmission line. They want you to find the current. So you can use your formula for power, assuming there is an ideal transformer. So we know that the power station has a power output of 100,000 watts, which is here. I convert it just to watts, not kilowatts. We know that the voltage from your cable in the secondary coil, because you can see that in your secondary coil, your voltage is 20,000. So they want to say, what is this current now? So my cable here has 20,000 volts. So what is my current that is in the cables now? Because this is where the secondary coil is. So we realize that the current is 5 ampere. Okay, so it's a much, much lower current. So they say, okay, in this case, you know your current. Can you calculate for me what's the power loss if you have this current and your cable has 5 ohm of resistance? Using P equals I square R, you can calculate. At the end of the day, there's only 125 watts being lost. But if you do not change it, you do not step up and reduce the current, you use this voltage here, your current will be very high, your power loss will also be much higher. Okay, you can do the calculation if you want. So with that itself, we will end on the topic of transformers. Thank you.